Today in the workshop, we're looking at non-volatile storage options for the ESP32. You'll learn how to use external flash, EEPROM, and FRAM to save data without power. We'll also learn two ways to use the ESP32's internal memory. And ESP32 never forgets, so welcome to the workshop. Well, hello and welcome to the workshop, and today we're going to be working with non-volatile memory for the ESP32. Now, by non-volatile, I'm talking about memory that does not lose its data when you take the power away, and there are a number of different types of NV memory that you can use with an ESP32. Now, I'm going to be restricting the conversation today to memory that is fixed in place, not removable memory devices like micro SD cards or SSDs, which you can certainly use with an ESP32. Instead, I'm talking about memory that stays as part of your project, data that does not go away even though you remove the power. Now, the ESP32 actually has some built-in NV memory. It actually has a fair bit of it, and for many applications, this is all that you're going to be requiring. But for some applications, the built-in memory is not suitable. It has a number of restrictions on its use, and we can add external NV memory to our ESP32, and we're going to be doing that as well. So let's go and take a look at the different types of non-volatile memory that there are for the ESP32. Non-volatile storage refers to memory whose data is retained after the power is removed. A non-volatile storage device requires no backup battery or capacitor. Data logging is a popular application for NV storage. You can use non-volatile storage to store settings and parameters. Another common application for NV storage is data buffering. And of course, large amounts of non-volatile storage are excellent for storing files. When we're talking about non-volatile storage for the ESP32, we can divide it into two categories, internal and external. The ESP32's internal non-volatile storage is managed by NVS. It was formerly managed by SPIFs, but this has now been discontinued. Externally, we can use EEPROM, external flash RAM, or for high-speed applications, we can use FRAM. Now, another form of non-volatile storage, of course, are micro SD cards. This removable media has very large capacities, a very low cost per byte, and makes use of the SPI bus. However, we won't be discussing removable media today. NVS and SPIFs refers to the onboard ESP32 flash memory. If you're using the expressive IDF, then you'll be using the NVS features. In the Arduino IDE, we use the Preferences library. For larger files, we can make use of the little FS file system. The legacy file system is called SPIFs, but this is no longer being used. One disadvantage of the ESP32's onboard storage is it has limited erase cycles, and so it can only be written and read so many times. In order to improve its lifespan, it employs automatic wear leveling. EEPROM is a classic storage method. It's inexpensive and very simple to use. EEPROM provides byte-level storage and retrieval. It has moderate speed, however it's relatively low capacity for its size. You can use EEPROM with a simple I2C interface. It has a reasonable number of erase cycles, a little under 1 million per device. One advantage of using EEPROM is its low power consumption. If you require more flash memory than the internal memory, you can add external SPI Flash memory to your ESP32. Flash is very inexpensive and has very large capacity. It uses the SPI interface and can be read very quickly. Writing the flash is not so quick, however, because it requires an erase before each write. As with the internal memory, it has limited number of erase cycles, and it requires wear leveling to maintain the flash memory's lifespan. FRAM is ferroelectric RAM memory. It's available with both I2C or SPI interfaces. FRAM has a very fast read and write time. However, it's a higher cost storage medium and it has a lower capacity because of its size. FRAM is excellent for buffering and data that changes rapidly. It has a virtually unlimited amount of erase cycles numbering in the trillions. FRAM also has very good data retention properties and it's measured in decades. There are many different applications for non-volatile storage within the ESP32, and your project can probably benefit from them. So let's start using NV storage with the ESP32. Alright, let's begin our discussion with the memory that is already built into your ESP32. Now, every ESP32 has built-in non-volatile flash memory, at least 4 megabytes of it, and some ESP32s have 8 or even 16 megabytes of this memory. And we can use this memory for a number of different purposes, for storing preferences and settings. We can use it for storing files, etc. There are some things like buffering that it's not very good at, because you can't really rewrite this memory too often. It has a limited lifespan. But for many applications, it's just perfect. Now, before we begin with this, I want to mention one thing, and that's SPIFs. You may, in your research, see some documentation about using the onboard memory using something called SPIFs, which is a file system. This is outdated information, and SPIFs is no longer used. Instead, it's been replaced by the preferences file and the little FS file system, which we're going to look at right now as we examine the internal memory in the ESP32. The ESP32's onboard memory is referred to as NVS, or non-volatile storage, and there can be 4 to 16 megabytes of it depending upon your model of ESP32. This storage is an excellent place for configurations and settings data. You can also make use of it for static images and web pages. Once again, if you run across SPIFs documentation, remember that this is depreciated, so don't use this for new designs. There are 2 libraries we can use for working with the onboard NVS memory. The Preferences library is good for name-value pairs, and the little FS library is great for saving and reading files. We're going to experiment with the onboard memory using a Arduino Xiao ESP32 S3 board, but you could use virtually any ESP32 for this experiment. We'll also be using a 10K potentiometer. We'll connect the wiper, or the center pin of the pot, to the A0 or analog 0 input on the Arduino Xiao. We'll connect one side of the potentiometer to the Xiao's 3.3 volt output, and the other side of the pot will be wired to the Xiao's ground connection. And that's it for the wiring. Now let's go take a look at a couple of sketches we can use with the onboard ESP32 memory. So the first demonstration with the built-in flash is going to use the Preferences library, and Preferences stores name-value pairs, and it's good for storing things like preferences and settings, etc. Now what we're going to do is we're going to store the value of the potentiometer, and then we're going to read it back every time the program boots up, so that way we can store it, we can unplug it, plug it back in, and it should retain the last value. So we're going to start off by including the Preferences library, which is already included when you install the ESP32 Boards Manager, and we'll define an object for it. We'll also define the potentiometer pin, and we'll go into the setup. We'll start the serial monitor, and we'll start the preferences, and then we're going to define a couple of variables to hold our value, the number of boots, the times we've booted up, and the last value in the potentiometer. And we're going to increment that value for boots, and then we're going to store that into memory, and we're going to store and we're going to look and see if we have a file in there, and if we do, we'll print out the last saved value in the pot, because remember, we're still in setup right now. We'll add a little delay so we can see that on the screen, and we'll go in the loop, and in the loop we're going to read the potentiometer value, and we're going to update it every 1.5 seconds, and we're going to put that into preferences, and we're just going to repeat that over and over. So what will happen again is we'll continually put that value into the preferences, and then we'll unplug this, plug it back in, and we should see the last value. So there's sort of two parts to demonstrating this. So let's load this up to the Arduino shell and watch it work. And so here's my experiment wired up on a very tiny solderless breadboard, and it's actually running at the moment. And so if we look at our serial monitor, and I move the pot around, we can see that I get the values. I go to one end, I get 4095, and we'll move it down to the other end. The values drop all the way down to 0. And so let's just put it somewhere in the middle there. Okay, so it's continually saving the value over here to the internal memory. Now let's go and pull the plug on it for a moment. Okay. And so let's plug it back in. And the last value it says is 1573, which indeed was the last save pot value. So it is working. It says I booted it 11 times so far, so you can tell how many times I've been fiddling around with it. So it does work as advertised, and it shows that it's pretty easy to use the preferences library to save data into the internal memory in an ESP32. Now, in order to demonstrate the little FS file system, I've actually created 3 bits of code, 2 of which I'm going to show you here, and the third one that you can just download from the dronebotworkshop.com article that accompanies this video. Now, the first bit of code writes data to a little text file that we're going to save in the flash memory using the little FS file system. The second bit of code that I'll show you soon reads that back so we can see that we've actually written something. And the third bit of code that I'm not going to demonstrate but you can download will just erase that text file so that if you want to start this from scratch you can do it. Now this is the code that's going to write data and append it to a text file, so it's going to continually make the text file grow. Now we're going to start by including the required libraries, the file system library and the little FS library. Both will have been included with your ESP32 boards manager, so nothing to download here. We'll define a pin for the potentiometer, and the name of the file that we're going to save to, we're calling it potlog.txt because it's logging the position of the potentiometer. Now we have a function over here that appends a line to that file, and so this is a good useful function to append the line to a text file. And then we're going to go into setup. In setup we're going to start our serial monitor. We're going to give some time delay for USB-C to come up, and then we're going to print the serial monitor. We're going to see if the file system exists, and if it does we're going to mount it. If not, we're going to format it on the first run. And then we're going to set the pin mode for the potentiometer. Now, if the file is new or if it doesn't exist, we're going to create it and write a header row to it. And then we're going to read back a bunch of parameters and go into the loop. Now, in the loop, we're going to go every second. We're going to get a value from the potentiometer, and we're going to append that to the pot log file right now. So we're going to append that line to whatever's in there. We're going to put the value in as the next line, and then we're going to print out to the serial monitor that we've done that, and we're going to go back and do it. And so every second we're going to write to that file. And so we're going to load this up, write to the file for a little bit, and then we'll unplug it, and then we'll run the second sketch to read back. Okay, I've got a little FS save demo running right now, and you can see on the serial monitor it's appending data, and I can change the value of that data by moving the pot around. And you can also see from the counter there, I've been running it for quite some time now. Okay, so we have ourselves some data. So now let's go and take a look at the second sketch here, the one that can read this data back. Okay, now that we've written to our text file, we need to read back from it, and that's what this code will do. And so the code starts off in a similar fashion to the last by including the same 2 libraries and giving the name of the file that we're reading from, potlog.txt. Then we have a function that dumps the contents of potlog.txt, and this is a useful function to have called dump file, and it'll take a look to see if the file exists, and if it does, it'll open the file, it'll read it, and it'll stream the entire thing reading out to the serial monitor. So it's a useful function for reading files in general, as is this function over here, which is a function that lists the root directory. So it basically does a directory of the root of the little FS file system, and looks at the partition, it looks at the directory, and prints that directory out to the screen. And so in setup, we're going to start our serial monitor. Once again, we'll give the USB-C some time to start off. And then we're going to take a look to see if the file is there, if the file system is there. If it isn't, we're not going to auto-format. So this is different than the last sketch in that this is false and not true. And this will cause it not to auto-format, because if it doesn't see that there, that means we probably didn't run the first demo, or the first demo didn't work. So we need to go investigate that. And then we'll get parameters as we did before and print them out. And now we're going to go and show the directory. So we'll call our list root function we just saw earlier. We'll print that out to the screen. We'll make a space in between. And then we'll go and we'll print out the file contents. We'll dump the file. And after that, we'll just print the monitor to say that we're done. And that's it. There's nothing that runs in the loop. So this will just run when it starts off and print the directory and the file content. So let's load it up and see if we can see what we saved in our non-volatile memory. And here are the results of our experiment. I'm getting the listing from potlog.txt, and as you can see, I've recorded a lot of data in it. This is the actual data that's inside the log file. And so it's read it all back. And it looks like it's working just perfectly. And so with these two different sketches, we can write and read using the little FS file system. And as I said, if you download the code from the article accompanying this video on the dronebotworkshop.com website, there's a third sketch there that will erase this text file so you can try it over and over again to your heart's content. So with all these different utilities, you're able to work with the internal file system in your ESP32. Now, the first type of external memory that we're going to be looking at is something that has been around for a long, long time. It's EEPROM, Electrically Erasable Programmable Read-Only Memory. And I have to admit that I'm old enough to remember what came before EEPROM, and that was EEPROM, less one E, Erasable Programmable Read-Only Memory. That was a sort of memory that actually was erased with ultraviolet light. You put a little sticker on the top of your chip to protect it from the UV light, and when you wanted to erase it, you put it into an eraser which had a bunch of UV lights. Now, this was a step up in allowing you to electrically erase these chips, and what these chips are mostly used for is data that doesn't change very much. Things like BIOSes and other things that you don't change very often are often stored into EEPROM. EEPROMs are very easy to use and they're very inexpensive, and if you want data retention on an EEPROM, it's measured in centuries, so your data is pretty safe. So let's go and take a look at what it takes to hook up an EEPROM to an ESP32. The EEPROM that we'll be using today is the popular 24LC256. This is a 256 kilobit or 32 kilobyte chip. It's an I2C device that can work up to 400 kilohertz. Its DC power supply can range from 2.5 to 5.5 volts, so this can be used with both 3.3 and 5 volt logic. There are 3 pins on the device that allow you to set its I2C address, so you can use multiple EEPROMs in the same circuit. The 24LC256 also features a hardware write protect pin. Programming for the EEPROM is quite easy, and we can do it all with the I2C wire library, which is built into the Arduino IDE. There are also a number of other libraries that can be used to make programming the EEPROM even simpler. The 24LC256 that we'll be using is an integrated circuit in an 8-pin DIP. Pins 1, 2, and 3 are the A0, A1, and A2 pins, which are used to set the I2C address. The base address of the device is hexadecimal 50. If you hold the write protect pin high, you'll prevent being able to write to the device. The pinout of the 24LC256 is as follows, with VCC or power on pin 8 and ground on pin 4. You can see pins 5 and 6 are used for the I2C bus. I'm going to be using the 24LC256 with an expressive ESP32 S2 development kit, but you could use any ESP32 for this experiment. We'll also require a couple of pull-up resistors. I'm using 4.7K resistors, but any value around that will work. We'll begin by connecting the 3.3 volt output of the ESP32 board to the VCC pin on the 24LC256 EEPROM. We'll connect the ground pin on the ESP32 to the VSS pin on pin 4 of the EEPROM. We'll also connect pins 1, 2, and 3 to ground. This will set the base I2C address to hexadecimal 050. And we'll ground the write protect pin on pin 7 as well, so that we can write to the device. Next, we'll connect pin 21 on the ESP32 dev kit to pin 5 on the 24LC256. This is the SDA line. Pin 33 on the ESP32 will be connected to pin 6 on the 24LC256. This is the SCL line. And finally, we'll connect 3.3 volts to one side of our pull-up resistors and the other side to the SCL and SDA lines. And this completes our wiring. Now let's go and take a look at some code we can use with our EEPROM. Now here's a sketch that we're going to be using to demonstrate our EEPROM, and it's pretty simple. What we're going to do is we're just going to create a string of text. We're going to write it into the EEPROM and then read it back. And so we're going to start off by using the wire library. It's the only library we need, the I2C library. We're going to do everything directly with wire in this sketch. Now we'll define some constants. The EEPROM address is hexadecimal 50, that's its I2C address, and the two pins that we've defined as SDA and SCL, and you can change these around if you're using a different ESP32. Most ESP32s allow you to use any two pins for I2C. Now we've got one of two functions. The first one writes pages to the EEPROM, so this is the EEPROM write page function, a very useful function that you can repurpose in your own code, and it just uses a string of wire commands. And same deal here, we're going to read a block from the EEPROM, so again a string of wire commands can accomplish that. So these two functions are something you could reuse when you're working with EEPROMs for another application. Okay, we'll go into setup. We'll start the serial monitor. We'll start the I2C at 400 kilohertz, and then we'll align to a page boundary. They have to be in multiples of 64, and so we'll set our base over here, and 40 is of course 64 in hexadecimal. Now we'll go and create a 32 value array and write into it, so that's this values from 1, 2, 3, 4, which is incrementing into an array. And we're going to write that array to the EEPROM using our EEPROM write page function we looked at earlier. And then we're going to go and read that back. And so we're going to use the EEPROM read block function we had earlier. And then we're going to cycle through the data that we read back and print it on the serial monitor. So we'll step up 32 times because we know there's 32 bytes of data inside there. We're going to print that out to the serial monitor, print another space, and then that's the end of that. There's nothing in the loop because everything happens in setup. So let's load that up and see if we can write and read from our EEPROM. And here's the setup on my solderless breadboard, and you can barely see the EEPROM chip. It's buried behind all of those wires, a lot of ground wires, just toward the side of the dev kit. And I've got this powered up, and I'm going to hit the reset button so that we can run through the setup again and see if we can get some results of writing and reading. And there we go, and here we are. We wrote 32 bytes, and we read back the 32 bytes and printed them out. Those were, of course, just incremented numbers that we saved. So everything seems to work correctly. We're capable of writing to and reading back from the EEPROM, and of course, with those two basic functions, you could pretty well do anything with this and your ESP32. Now, earlier in the video, we looked at the internal flash memory in the ESP32 and saw how it was really good for storing things like preferences as well as files. And the only thing about that memory is that you might not have enough of it. There's at least 4 megabytes in your ESP32, but remember, an ESP32 can be used, among other things, as a web server. And web servers often have images and other files that take up quite a bit of space. So you might need a little bit of extra flash memory. Well, if you do, you can add extra flash memory over the SPI bus. And so let's go and take a look at what it takes to add a flash memory module to our ESP32. The external SPI NOR flash device that we're going to be using today is the W25Q64. This is a commonly available 64 megabit or 8 megabyte flash unit. It uses the SPI bus and can use high clock rates. It works on a 2.7 to 3.6 volt supply, so it's excellent for 3.3 volt logic. And it also has a hardware write protect pin, although not all modules expose this pin. To program the SPI NOR flash, you can use the built-in SPI library. There are other libraries you can use as well in order to simplify programming with this flash memory. The W25Q64 module has the following pinouts. VCC is 3.3 volts in, CS is the chip select, DO is the data output, GND of course is the ground, CLK is the clock, and DI is the data input. We're going to be using this flash memory with an ESP32 S3 dev kit, but again, any ESP32 device will work. We'll connect the DI or data in pin to GPIO pin 11 on the ESP32. The clock or CLK pin will be connected to GPIO pin 12. GND will be connected to the ESP32's ground. The DO or data output will be connected to GPIO 13. CS or chip select will be connected to GPIO pin 10, and we'll connect the VCC pin to the 3.3 volt output from the ESP32. And that's it for the wiring. Let's take a look at some code we can use to test out our SPI NOR flash device. Now here's a sketch that we're going to use to demonstrate the use of the flash memory that we've connected to the ESP32, and tells you up over here in the header what we're going to do. We're going to read the ID because there's an ID byte, a manufacturer's ID, in every bit of this memory, so we can read that back. We can also read back the capacity, and this one should be about 8 megabytes. We're going to erase a 4 kilobyte sector, and then we're going to write and read some text into and out of the memory. And so we're going to start off by including the required libraries. Now, the SPI library is included with your Arduino IDE, but you're going to need to load the SPI memory library from your library manager. So go up to Library Manager and look for that and load it. We'll define the pins that we're using for the SPI bus over here, and then we're going to start the SPI Flash object over here against the chip select pin. And now we're going to go into setup. We're going to set up our serial monitor, and we're going to begin our SPI bus, and we're going to define the beginning of it over here. And they're going to check to see if the flash is started, and if it is not detected, we'll print out over here. Otherwise, the flash is ready to use. And then we're going to go and get some parameters from the flash memory, and this one over here returns what's called a JEDEC number. It's a JEDEC ID number, and every flash memory chip will have a different one. So we'll print that out. We'll print out the manufacturer number, the memory type, and the capacity of it. So all of these are things that we can get from that get JEDEC ID. Then we're going to format that and print it out to the serial monitor. Then we're going to go and erase a 4 kilobyte sector over here. And so we're going to do a sector starting at this address. And then we're going to go and create a string, and we're going to write that string, that character array, into the flash, and then we're going to read it back from the flash, and we're going to print out what we've read back and the parameters over here, and then we're just going to finish, and that's it. There's nothing in the loop because it's all being done in setup. So let's go and load that and see if we can get the parameters from our flash memory. And here's my demonstration all ready to go. You can see the SPI memory module up here, and of course my ESP32 S3 dev kit down here. And I've got the serial monitor all prepped. All I have to do is plug the USB cable into the UART connection. And we do that, and we got our quick test over here. And if we look at the bottom, we can see that it gave us the JEDEC ID of the SPI memory chip. It gave it its capacity, which is about 8 megabytes. And it says it's erasing the sector. It wrote okay, it read back okay, and it printed out the data that it read back. So it does seem to work pretty well. And that was a simple test, but with the functions provided there, you can use SPI memory within any of your ESP32 projects. Now, the final type of memory that we're going to be looking at today is FRAM, Ferroelectric Random Access Memory. And FRAM has undergone a bit of a revival these days. It's certainly not new. In fact, the module we're using actually predates the ESP32 itself. But because of today's number of battery-powered and IoT equipment, FRAM is getting a new lease on life. It's very, very fast, non-volatile memory. So let's go and take a look at what it takes to add FRAM to our ESP32. The ferroelectric RAM chip that we're going to be using is a popular breakout board, the MB85RC256V. This is a 256 kilobit or 32 kilobyte ferroelectric RAM. It runs on the I2C bus at speeds up to 400 kilohertz. It can use a power supply from 2.7 to 5.5 volts, so it's compatible with both 3.3 and 5 volt logic. You can set it for multiple I2C addresses using the A0, A1, and A2 pins. If you ground all of these pins, the base I2C address will be hexadecimal 50. The board also has a second I2C address, a device ID address at hexadecimal 7C. You can work with the FRAM using the wire library, the built-in library for working with I2C. There are also additional libraries that you can use with the FRAM. To demonstrate the ferroelectric RAM, we're going to pair it up with a BME280 pressure, humidity, and temperature sensor. We're going to drive everything with an ESP32 C6 dev kit, but any ESP32 will work. We'll begin by connecting 3.3 volts from the ESP32 to the VCC on the FRAM and the V-in on the BME280. We'll connect the ground of the ESP32 to the ground on both of the boards. GPIO pin 11 on the ESP32 will be connected to the SCL pin on the FRAM and the SCK pin on the BME280. Note that the BME280 can be operated in both I2C or SPI mode, and we're operating in I2C mode. And GPIO pin 10 on the ESP32 will go to the SDA on the FRAM and to the SDI pin on the BME280. We'll also ground the remaining pins on the FRAM, the write protect and the 3 address pins. And this completes our wiring. Now let's go and take a look at some code we can use to demonstrate the ferroelectric RAM. Okay, now here's a demo that we're going to be using with our FRAM, and I've got it listed out here what it's going to do. Essentially what it's going to do is going to start up and see if there is any data in the FRAM, and if so, it's going to display it. Now what that data will be temperature data from the BME 280, because what it's going to do in the loop is it's going to read that and write it back to the FRAM very quickly, about every 200 milliseconds. And so essentially when we start up, we should see the last valid temperature written there. Otherwise, when it's running, we should see it continually write. And the reason this demonstrates a FRAM very well is that at the rate it's going, about 5 every second, if we were using the built-in memory in the ESP32, we'd burn it out pretty quickly. At that speed, we'd go maybe about 6 or 7 hours before it burned out. If we were using an EEPROM, we could go a little bit longer. It would probably go about 2 or 3 days days before it burned out. But since we have trillions of write and read operations in our FRAM memory, it's not an issue. We could go for years and years and decades doing this and it won't burn out the memory. So basically we're writing and reading very quickly. Okay, we're going to start off by including the required libraries, and there's a couple that you're going to have to get. The Adafruit FRAM I2C library, which you can get in the library manager, and the Adafruit BME280 library. Now this Adafruit sensor one is part of the Universal Sensor Library, which is installed with, I know, the BME280 and maybe with this one as well. If you've been using Adafruit devices, you probably already have, but anyway, the Universal Sensor is pretty well installed for almost every Adafruit device. Then we go in and define the pins we're using for I2C. Of course, if you want to use a different ESP32, just change those around. And we're going to define objects for the FRAM and the BME280. And we're going to define the address that we're going to be using to store our temperature value within the FRAM memory. Now, in the setup, we're going to set up our serial monitor and print to it. We're going to initialize the I2C bus, and we're going to initialize the FRAM, and assuming that everything is okay, we'll get down here, we'll initialize the BME280, and then we're going to go and take a look to see if we actually have data. So we're going to clear the last temp value, and we're going to read from that address in the FRAM to see if we have a value, and if we do, we will print it out. If we don't, we'll mention that there's no previous data found in the FRAM. So we're going to print that out onto the screen. I'm going to put in a slight delay and then end off the setup. And so that way, when we start it off, we should see the last value printed out to our screen. Now in the loop, we're just going to read the temperature from the BME, and we're going to print that out on the screen, and we're also going to write that over here to the FRAM, and then we're going to delay a very short amount of time and do it over and over again. So we're rapidly going to write that into the memory chip and read it back every time we start to sketch. So let's run the sketch for a little bit, then we'll stop it and run it again and see if it logs the last value from its FRAM memory. Okay, and here's my demonstration wired up onto a solderless breadboard. You can see the BME280 at the top and the FRAM module at the bottom on the bottom left, and of course my ESP32C6 dev kit. Going to plug my cable into the UART connection. And everything boots up, and it reads out the last known temperature that it recorded, and it starts recording some new temperatures, and I'll let it record a few temperatures for a little bit, and then we can stop it and start it again. Okay, let's pull the plug on it. And let's start it again. And it reads back the last temperature that it wrote, and it continues to rate temperatures. And as I said, we can run this for years and years. It'll continue to work, whereas if we were using a different type of memory, we would eventually burn it out because we'd exceed the number of read-write cycles. But FRAM memory has read-write cycles in the trillions. So FRAM is really great memory if you need fast memory that's non-volatile, and I'm sure that it or one of the other solutions that we've seen today will satisfy any of your NV memory needs for your ESP32 projects. And so that wraps up our look at non-volatile memory for the ESP32. I hope that you enjoyed the video and that's inspired you to use non-volatile memory in some of your ESP32 projects. Now, if you'd like more information about NV memory, or if you want to grab the sketches that I used today, you will find all of that on the article that accompanies this video on the dronebotworkshop.com website, and there's a link to that article right below the video. While you're on the website, if you haven't yet, please consider signing up for my newsletter. It's just a way that I can let you know what's going on here in the workshop, and sometimes even give you some previews of my next video. Signing up is free. All you need to do is give me your email address. If you're also willing to give me your first name and make up a cool username, you can also sign up for the DroneBot Workshop forums. The forum is a great place to talk shop with a number of like-minded individuals who can help you out with your project, or maybe you can help them out with their projects. And of course, the forum EEPROM is free. And another thing that is always free is to subscribe to the YouTube channels. I make videos about microcontrollers and electronics, and if you enjoyed this video, you'll probably like my other ones. Signing up is very easy. All you need to do is click on the subscribe button and also click on that bell notification. And as long as you've enabled notifications in your web browser, you'll get notified every time that I make a new video. So until we meet the next time, please take good care of yourself, stay safe out there, and I'll see you soon here in the DroneBot Workshop. Goodbye for now.